Hello dear students, welcome once again to heat transfer course. So today we are supposed to conduct the fifth session of the first unit, heat transfer by conduction. Hope you can remember what and all we studied in the first four classes. So I'll just take you through the discussions held in the previous class. So in the last class we derived a rate of heat transfer equation for steady state conduction through a composite wall. So we saw the examples of this case of heat transfer, and also we applied the Fourier's law to derive a rate equation. For the today's class, I am taking up the conduction through cylindrical wall. That is how steady state heat flow occurs through a cylindrical wall, where we come across such case of heat transfer. So just like we did in the previous case, here also we are going to apply Fourier's law of heat transfer to derive the rate equation for conduction through cylindrical wall. So, a case of conduction through cylindrical wall arises in many situations. For example, when heat flows through the wall of the pipe having a circular cross section. So, that is a typical case of conduction through cylindrical wall. So, also, whenever a cylindrical vessel is being used for heating a fluid by means of circulating hot fluid in the jacket that surrounds the vessel. So if the heat has to flow from the fluid in the jacket to the fluid inside the vessel, then it has to pass through the wall, and that is also a case of heat flow through cylinder. Okay, so this is how we can visualize conduction through a cylindrical wall. So this is the front sectional full view of a cylindrical pipe that is carrying some hot fluid. So imagine that it's a thick walled cylinder having an inside radius R1 and an outside radius R2. Assume that the inside wall temperature be T1 and the outside wall temperature of the pipe be T2. Assume that T1 is greater than T2. That means the fluid inside is at a higher temperature. So as a result of that, the inside surface becomes hot. So since T1 is greater than T2, we can expect the heat to flow from inside of the cylinder to the outside, passing through the metal wall. Assume a thin cylindrical element of radius r that is concentric with the main cylinder. Also assume that the cylindrical element is having a thickness dr. Okay, so this is a 3D view of the flow through cylinder. So this is the outer wall of the cylinder, inner wall of the cylindrical pipe. Now, so here the notations taken are a bit different. Inside radius is Ri, outside radius is Ro, inside temperature is Ti, outside temperature is To. So as Ti is greater than To, we can expect the heat to flow from inside to the outside of the pipe. So as indicated by the red colored arrows in the diagram. Okay. Assume that the length of the pipe be L meters. So now the area of heat transfer for the given situation is A equals 2 pi RL. So as I said already, we have considered a thick walled cylinder of inside radius R1 and outside radius R2. And we have assumed L to be the length of the cylinder. Also let K be the thermal conductivity of the material of which the cylinder is made. Let the temperature of the inside surface be T1 and that of the outside surface be T2. Assume that T1 is greater than T2 and hence heat flows from inside of the cylinder to the outside. Consider a very thin cylindrical element. So this I have already explained. So a thin cylindrical element is considered at radius r, that is concentric with the main cylinder, such that this element lies in between the distance r1 and r2. Okay. Consider that the cylindrical element is having a small radius dr, so small thickness dr. So let us consider the fundamental equation for conduction. So you know this is the Fourier's law equation. Q equals minus Ka dt by dx. dt by dx is the temperature gradient. A is the area of heat transfer. K is thermal conductivity. Q is the rate of heat transfer. The above equation for rate of heat flow at a radius r can be integrated as Q equals minus K. A in this particular case it becomes 2 pi RL dt by dr. After you rearrange this equation, dr will get shifted to left hand side, q will get shifted to the numerator of the right hand side. So k2 pi L divided by q being constants can be taken out from the integration sign. So the limits of integration is when r equals r1, t equals t1, when r equals r2, t equals t2. Shift the dr sign to this side, keep the dt to this side. So dr along with the r here. So that r gets transferred to the denominator on the left hand side. So integrate between r1 to r2, t1 to t2. So it becomes ln r2 by r1 is equal to minus k2 pi L into t2 minus t1 divided by k q. So shift that q to the left hand side. Finally, the equation becomes q equals k2 pi L into t1 minus t2 whole divided by ln r2 by r1. So keep this as equation number 5.2. Equation 2 can be used to calculate the flow of heat through a thick-walled cylinder, which can be put into more convenient form as follows. So Q is equal to K2 pi, that ln R2 by R1 can be written like this. We can replace the ln R2 by R1 by R2 minus R1 in the denominator and introduce a term Rm in the numerator. So this equation now is equation number 5.3, where this Rm is called the log mean radius for the thick-walled cylinder. Okay. And this Rm is given by R2 minus R1 divided by ln R2 by R1. And this entire term 2 pi RML will become AM, the logarithmic mean radius. Okay, we can write the Rm equation like this. Rm is equal to R2 minus R1 divided by ln R2 by R1 equals R2 minus R1. We can write this down as divided by 2.303 log R2 by R1, or simply R2 minus R1 divided by ln R2 by R1. So let this equation be 5.4. So as I told you, AM 2 pi RML can be written as AM, the logarithmic mean area. So now the final equation has been arrived at, um, and it is Q equals KAM T1 minus T2 divided by R2 minus R1. So this is your equation number 5.6. So further, you can write the equation as Q equals T1 minus T2 divided by R2 minus R1 by KAM. So this entire term in the denominator represents the resistance to heat flow in the present case. So then the equation is of the form rate equals driving force divided by resistance. So delta T is T1 minus T2 and R is R2 minus R1 divided by KAM. So where R, capital R is equal to small r2 minus small r1 divided by KAM. So in case of thick walled cylinder, this log mean radius give you the correct rate of heat flow. So whereas if the wall of the cylinder is thin, then we can go for arithmetic mean radius for calculating the rate of heat transfer. So in that case, arithmetic mean can be used without any appreciable error. Okay, so let us now go through multiple choice questions. The dash radius will give the correct rate of heat flow through thick walled cylinder. Is it geometrical mean radius? Is it arithmetic mean radius? Is it log mean radius? Is it none of these? Okay, just now we learned that in the equation to find out the rate of heat transfer through thick walled cylinder. So we are supposed to use logarithmic mean radius. So option C is the right choice. In case of thin walled cylinder, the dash mean is used without an appreciable error. So in case of thick walled, as you just now seen, you have to use log mean radius. But if the wall of the cylinder is not that thick, then you can easily use the arithmetic mean radius, that is R1 plus R2 divided by 2. So out of the four options here, option A is the right answer. R is equal to dash divided by KAM. So what should come in the numerator? Is it R2 minus R1? Is it R1 minus R2? Is it RM2 minus RM1? Is it none of the above options? So R2 minus R1 is the right answer. In the equation Q equals K2 pi RML T1 minus T2 divided by R2 minus R1. Rm is known as arithmetic mean radius, geometric mean radius, logarithmic mean radius, none of these. Okay, for thick walled cylinder, the Rm value is the log mean radius. Heat loss through the wall of a pipe of circular cross section is a case of steady state conduction through plane wall, steady state conduction through composite wall, steady state conduction through a cylindrical wall. None of the above. So it is a case of steady state conduction through cylindrical wall. So option A is the right answer. So with that, we have come to the end of the fifth class of heat transfer by conduction. So in today's class, we learned in which cases heat flows through a cylindrical wall and how we can calculate the rate of heat transfer for this situation of heat transfer. So thank you for listening to me. Let us again meet in the sixth session.